Good afternoon to one and all present here. I am Pratap Mangol. Was a student, just graduated from Army College of Engineering, and this is my paper which I will be presenting. Design of an S-band transmit mode active integrated antenna for low power IoT application. The authors of this paper are Pratap Mangol, myself, Dr. Mahesh A, Dr. Jogesh Chandra Dash from Indian Institute of Science, and Dr. Dedeep Sarkar, also from Indian Institute of Science. So today's presentation will be as follows. We will start with the introduction, the problem statement, design of the active integrated antenna. There are two parts to it. One is the negative impedance converter, then is the Wozniacki antenna or the radiating structure. Then the results and discussions, and finally we will come to the conclusions. So now we are all used to traditional antennas, which are passive reciprocal devices. They can be used for both transmitting and receiving. Now, active integrated antennas are a special class of antennas wherein we have an active circuitry also integrated into the radiating structure in order to increase or extend the functionality of the antenna. Now, most of these transmit mode active integrated antennas come in two flavors. One is transmit mode AIS, which have an oscillator integrated into them, or the other is ones which have power amplifiers integrated into them. So both of these are used for spatial power combining purposes. Now we will be specifically focusing on the oscillator variant of such active integrated antennas, and the way such oscillators are formed is either by placing the antenna inside a feedback loop, positive feedback loop to maintain sustained oscillations, or the other one is to have a cross-coupled pair if you are having somewhat like 1x2 array cells, or the third one, which is the topology we will be following, is by connecting a negative impedance converter to the antenna. Now this NIC approach has certain advantages, the most prominent of which is that it has a lower occupied area, meaning it has a smaller footprint and it is more suitable for IoT applications. Now, because these active integrated antennas have an active circuitry along with the radiating structure, they are self-contained in nature and they have been shown in multiple places to be used for frequency translation within Wi-Fi bands or for other IoT application. And this is prominently done by including mixing functionality. Now, since we are targeting the arena of low power IoT devices, we are focusing on the realm of IoT backscatter based communication, wherein the IoT device does not actually transmit a signal but modulates data by reflecting any incident illuminating signal on it. Over here, we are proposing the implementation and utilization of active integrated antennas to be the source for generating illuminating signals for low power IoT devices. So most common literature utilizes standard NAV equipment, any synthesizer or vector signal generator for the illuminating source. We are trying to replace that for field deployments with active integrated antennas. So this brings us to the problem statement, which is to design and develop a compact, low-cost S-band source which generates the excitation signal for backscatter communication. So this brings us to the topology of our active integrated antenna. So there, from a system level point of view or from a block diagram, what we can see is that we essentially have two parts to this active integrated antenna. The first one is the main radiating antenna, which is modeled as a lossy resonator, and in order to maintain sustained oscillations and replenish the energy which is lost due to radiation, we have a negative impedance converter. This negative impedance converter is formed by connecting our transistor with a suitable and stable termination, such that when we see this gamma out over here is supposed to be positive in nature, greater than 1, which signifies more energy is being sent outwards, that more energy is being reflected than what is being sent in. So the topology chosen from a circuit level point of view is we are using a common base topology for the negative impedance converter, and in order to make this, to destabilize the entire architecture, we are having a series degeneration inductor over here. The entire prototype is designed to work, since we are also targeting it to be low cost. It is designed to use 0.6 mm FR4, and the material properties is dielectric constant of 4.4 and a loss tangent of 0.011. This is in accordance with the board house we have chosen for fabrication. Now, for this topology which we have, the value of this destabilizing inductor is very critical, and the way we characterize the degree of instability, qualitatively at least, is with the Rowlett stability factor. And we have to also ensure, we have to select this LD-stab value so that we have a much lower Rowlett stability factor, which signifies it's highly unstable in nature. Now, speaking with some of the other specifications for the design, we need to have a power dissipation to be less than 100 milliwatts, and this corresponds to a current to be less than 30 milliamps. Sorry. And from our DC point of view, we will be using a resistor divider bias along with the distributed element bias T to minimize component count. So, moving on to the bias T design. So for the bias T design, we have gone ahead with 2 quarter wave sections. Since we are in S-band, we are choosing 2 and 3 gigahertz. So we have 2 quarter wave sections where the L1 length corresponds to lambda by 4 at 2 at 3, and L1 plus L2 corresponds to lambda by 4 at 2 gigahertz. And we have 2 radial stubs also present over here to create the isolation. So this is the simulated S parameters over here. We can see around 2 gigahertz, much lower than 2 gigahertz itself. We start with the roll off, and the S21 at around 2 gigahertz is around minus 22 dB or so, and the S11 is close to 0, which shows that we are having proper isolation between the DC and RF paths. Now, combining the previous shown distributed element bias T with the topology, this is the transmission line diagram of the NIC. And in order to determine the most suitable value of the destabilizing inductor, which is realized by a short section of a shorted transmission line, we run a parametric analysis in Cadence AWR itself, and this is the plot obtained of the Rowlett stability factor with respect to the inductance value in nanohenries. From the plot, we can see a value somewhere close to 4 or so nanohenry gives us the lowest value of the Rowlett stability factor. But since this value is very close to the parasitics which are going to be encountered, we move somewhere around 15 nanohenries, which provides a much smaller trade-off, but still results in a sufficiently unstable device for oscillations. So for the chosen transmission line parameters, a value of 50 nanohenry corresponds to 16 millimeter on our chosen substrate. So simulate after layout and performing parasitic extractions. This is the Z parameters of the impedance converter, and from the shown Z parameters, we can see that the negative impedance converter exhibits a self-resonant or self-oscillating frequency for a 50 ohm load at 2.477 gigahertz, which is within S band. And to tune it to be within the range of operation what we require, the radiating structures reactance has to be compensated or adjusted. So this entire thing with parasitic extraction has again been carried out with Cadence AWR itself. Now moving on to the radiating structure, which is the second part of our active integrated antenna. We have gone ahead and chosen a quasi-Yagi antenna, and this is the drawing of it. So the quasi-Yagi antenna consists of a single director element over here, a radiating dipole, and this ground plane also functions as the reflector element. Since the dipole has to be differentially fed, we have gone ahead with a microstrip to slot line transition, and the slot line is what is feeding the dipole, because the slot line is inherently a differential feed, which we are using over here, again to minimize component cost and also to maintain planar structure with a small footprint. So for the given structure, we can draw an equivalent transmission line diagram over here, with the transition being represented by this transformer over here, and we are having a double stub matching over here to improve the bandwidth. A part of it is an open stub in the microstrip region over here, what we can see, and we have 2 small shorted stubs of different transmission line characteristic impedances implemented with the slot line. So now that we have seen the 2 individual elements, which is the radiating structure and the negative impedance converter, we'll be focusing on the results part. So first we'll be showing only the quasi-Yagi radiating structure, the S11 and radiation pattern, and then we'll be showing the complete integrated AIA test, both in open air and in the anechoic chamber. So from the single quasi-Yagi antenna tests, we can see that we had a simulated gain of 5.88 dBi, but we have a measured gain on 4.86 dBi. We had a simulated half-hour beamwidth of 140.6 degrees and a measured half-hour beamwidth of 93.6 degrees. The bandwidth what was simulated was 1.08 gigahertz, but the measured bandwidth is 1.25 gigahertz, slightly larger, and the other parameters are slightly smaller. This quasi-RV antenna was designed and simulated in ANSYS HFSS, and these are the corresponding patterns of the return loss and the radiation pattern, both E-plane and H-plane cut. Now moving on to the open air test. So the open air test was carried out in this procedure. They were placed with 45 centimeter separation. We have a 30 centimeter scale for scale. This is the negative impedance converter. This is the quasi-RV radiating structure, and we are keeping another quasi-RV just to connect it to the spectrum analyzer for measurements. We can see that we are receiving a power of minus 17.5 dBm. In the next slide, I will be showing you the similar setup but in an anechoic environment, and over here we are able to characterize the transmit power and the EIRP. So in the anechoic chamber test, we have kept it at a separation distance of 3.75 meters. This is in the far field. The receiver horn antenna gain is 10.25 dBi, and the received power from the power meter over here is minus 30.5 dBm. So back calculating with Fritz's transmission formula, we get the transmit power to be 5.04 dBm from the AIA, and the effective isotropic radiated power of the AIA is 9.9 dBm. So to conclude, the designed AIA does indeed operate in S-band at 2.16 gigahertz. The active antenna has a gain of 4.86 dBi and a transmit power of 5.04 dBi, and the AIA showcases an EIRP of 9.9 dBm. This is on par with current trends reported in literature, which have showcased 8.9 dBm in reference 6, 12.5 dBm in reference 7, and 11.5 dBm in reference 25, most of which are in transaction papers or other conferences as indicated. The total measured power dissipation is 93 milliwatts, and the DC to RF efficiency is 3.42%. And it can be conclusively shown that the designed AIA can be used as an excitation/illuminating signal for wireless backscatter communications, which is predominantly used for low power IoT applications. So this brings us to the end of the talk. These are some of the references which we have. And finally, we'd like to thank Indian Institute of Science for providing us the opportunity to continue and carry out our research and to even present this work over here. Thank you very much. Open for questions now.